Okay, can everybody see my screen? This is Horribly Extensive Chemistry 111 Final Exam Review. All right, perfect. Yeah, so this review was penned by the chair of the department. And let's take a look at it here. First question says, given a list of compounds, determine which name is correct. So which combination is correct here? We have zinc sulfide, sulfur, something fluoride, so on and so forth. Well, we're looking for the one that is correct. I notice a problem in zinc sulfide right away. You remember that in the transition metals, there are 3 of them that only have 1 charge. For example, zinc is always 2+, cadmium is always 2+, and silver is always 1+. And so this would not be zinc sulfide. Zinc sulfide, so since zinc always has a 2+ charge and sulfide is always a 2- charge, zinc sulfide is actually ZnS like that. The problem with the next one, it says sulfur 6 fluoride. Sulfur is a non-metal. It's not a transition metal, and so we don't have to use the stock naming system. This is simply a covalent compound. This would be sulfur hexafluoride, fluoride. I'm trying my best to spell here. There we go. The next one, vanadium tribromide. I see a problem with this one because vanadium is a transition metal. And so for this, you do have to use the stock naming system. Now, bromide is always Br-, and you have 3 of them. And so this compound would be vanadium 3 bromide, okay? And the last one says titanium 3 oxide. That one is actually correct, right? Because oxide has a charge of 2-, and it says that our titanium has a charge of +3. So if we have titanium with a 3+ charge and we have 2 of those, that's going to give us an overall charge of +6. And if we have 3 oxides, that gives us a charge of -6, right? -2 times 3. Anyhow, I think you get the idea. So those balance out. And so this one is correct, titanium 3 oxide. All right, the next problem is just a nomenclature problem. We're given a formula and we're asked to name the compound. Notice this is an ionic compound because titanium is a metal. Sulfate is a polyatomic ion that you have to be familiar with. And sulfate is completely comprised of non-metals. So you know that sulfate is a charge of 2-, and we have 2 sulfates. So if we take 2- and we multiply it by 2, overall that gives us a charge of -4. That tells us the charge on our titanium is +4. And so this would be titanium 4 sulfate. Titanium 4 sulfate. All right, next, just given a formula in which the identity of one of the compounds is unknown, determine its identity. So if the formula is XCl or XCl2 or XCl3, well, everybody should know that chloride is a halogen, or chlorine is a halogen. It's a group 7A. All the halogens like to take on 1 more electron to develop a -1 charge so that they could become isoelectronic with the neighboring noble gas. And so, for example, if you had XCl, that would mean that your X has to have a +1 charge. It would be a group 1A metal like lithium or sodium or potassium. We could put here lithium or sodium, right? And I should put in my charges here. Anyhow, it could be, again, could be potassium or rubidium or cesium. The next one, XCl2, that would have to come from group 2. So it could be, you know, for example, it could be magnesium with a 2+ or calcium with a 2+ charge, right? And the next one, if it's XCl3, well, that's got to have a +3 charge, so it's going to come from group 3. It could be, you know, it could be aluminum 3+. It could be boron trichloride, whatever. All right. Given a list of ionic compounds, determine which would have the lowest melting point. Remember Barbie. So Barbie this is something that Dr. Garcia came up with. So if you have the electrostatic force is proportional to the charge of your cation times the charge of your anion divided by the radius, right? The one that's going to have the strongest force, okay, is the one that's going to be the most like Barbie. Now, again, this is something that she came up with, not me, okay? I had to ask her what it means. And she said, well, Barbie is big on the top and small on the bottom. So that means if you have a big numerator and a small denominator, that the electrostatic force is going to be strongest. Now, if we're looking for what's got the lowest melting point, it's going to have the weakest intermolecular forces. And so I can kind of redeem myself from the practice exam we looked at the other night, right? We're looking for what's got the weakest intermolecular forces. So what does that mean? It means we're going to want this to be small, and we're going to want this to be large. Okay, so the opposite of Barbie. All right, well, if we look at these four compounds here, you see the strontium comes from group 2, and so it's got a +2 charge, whereas sodium comes from group 1A, and so it has a +1 charge. So that's going to eliminate number 1 and number 2, because in all of them you have a chloride or an iodide, and those all have a charge of -1. So that leaves us with these two right here. Now, if we want it to be large on the bottom, you know that as we go from fluorine to chlorine to bromine to iodine, as we go down the group, the elements get larger, right? As the principal quantum number increases. And so the one that's going to have the smallest charges and the largest radius is going to be sodium iodide. That's going to result in the weakest electrostatic interaction between the cation and the anion, and result in the lowest melting point. All right, number 5, it says, given a list of compounds, determine which has covalent bond. And her hint is, if it has a metal or a transition metal, it's ionic. Just get rid of it. So we're looking for a compound here that has predominantly covalent bonds. Well, titanium is a metal, a transition metal, as is palladium, and barium is a metal as well. Right, barium is in group 2A, but it's on the left-hand side of the metalloid line, and so it's considered a metal. And if you look at carbon diselenide, okay, carbon and selenium are both non-metals. So we'll put here, both are non-metals. Therefore, this is a covalent compound. Okay, the rest are all ionic. So all of these are ionic compounds. Okay, you should know the definition of an isotope. It's got the same number of protons, but a different number of neutrons. So if you were given a bunch of choices here, it says which of the following are isotopes, and you could spend some time looking at this. I mean, these aren't even the same, right? Nitrogen, the element, and nitrogen, the molecule. Here, it's not the same, right? You got an element and a compound. Here you have an ion, so that's not right. Here you have two elements that are completely different. But if you look over here, you have carbon 14 and carbon 13. These are in fact isotopes, right? Same element, but different number of neutrons. If we compare the two, carbon 14 and carbon 13, and we look at the number of protons and the number of neutrons, well, remember, the number of protons is what governs the identity of an element, and carbon is element number 6. So both of these have 6 protons, but remember that the mass number is the sum of protons plus the number of neutrons. And so we must have 8 neutrons for carbon 14 and 7 neutrons for carbon 13. All right, let's take a look at the next one. It says, given mass in percent abundance of one isotope and percent abundance of another isotope, determine the mass of isotope 2. This is a very specific problem, okay? It says bromine is naturally occurring as a mixture of 2 isotopes. Okay, one isotope has a mass of 79 atomic mass units and a relative abundance of 50.69%. What is the mass of the second isotope if its relative abundance is 49.31%? Well, if you look in the periodic table, the mass, or the molar mass given for bromine is 79.90. So I'm going to write that down, 79.90 AMU. But remember, that's a weighted average of the 2 isotopes. So how would we set this up? Well, we know that the first isotope has a mass of 79 and it has a relative abundance of 50.69%. I'm going to divide that by 100 to make it a fraction out of 1. So if I multiply that by 0.5069, and then I tally up the mass of the second isotope that I'm going to call X, and I multiply it by its relative abundance, which is 49.31, so 0.4931, like that. Then all it is a matter of a little bit of math to solve for X. Okay, just a little bit of math to solve for X. And we get the X times, X, and I've already done the math here, X times 0.4931 is equal to 39.85 atomic mass units. And so that you get that X is equal to 80.82 AMU, which makes sense. Now, since I only have 2 sig figs here, I guess I should only have 2 sig figs in my final answer. So that would mean that it's 81 AMU, which is correct. Okay, so 81 AMU. Anyhow, there we go. Number 8, calculate the number of protons, neutrons, and electrons. We've already looked at that this evening. Remember that protons give the identity of the atom or ion. Neutrons are found by subtracting the number of protons from the mass number. And electrons, well, if it's negative, you add extra electrons, and if it's positive, you subtract them. Remember, electrons are negative, right? So don't get caught in the trap of, well, if it's positive, I must add more electrons. No, absolutely not. Okay, it's asking us a question here. How many protons, neutrons, and electrons are present in calcium-40 with a 2+ charge? Well, we can go ahead and add the atomic number because that never changes. If you look at the periodic table, calcium is element number 20. And so we know the number of protons is going to be equal to 20. Now, this number here is the sum of the number of protons and neutrons. So that means that it's going to have 20 neutrons. Now, what about electrons? Well, normally in a neutral atom, the number of electrons is going to balance out the number of protons, which would be 20. But if I have a +2 charge, that means I would have lost 2 electrons, which would mean I would only have 18 electrons left over. And so the correct answer would be B, 20 protons, 20 neutrons, and 18 electrons. Number 9, have a conceptual understanding of the relationship between empirical and molecular formula. Having the same empirical formula does not mean you have the same compound. For example, let me give you an example here. Okay, well, the example that she uses is the one I was going to use. It says formaldehyde has a formula of CH2O. Acetic acid is C2H4O2. It also has an empirical formula of CH2O. I'll give you another one. What about glucose? C6H12O6. It also has an empirical formula of CH2O. Okay, all of these have the same empirical formula, but they're all different compounds: acetic acid, formaldehyde, and glucose. Having the same empirical formula doesn't mean you have the same number of molecules, does it? All right, so something to think about, and let's move on to the next point, which is number 10. So you can see that some of these are questions and some of them are more just discussion points. Number 10, given an element, determine which is more similar to it. Which one of these elements would be most similar to magnesium? Well, if you look in the periodic table, magnesium is found in group 2A. So group 2A. And remember, the elements that are in the same group, sometimes we call groups families. And why do we call them families? Because people in the same family have a tendency to resemble each other. So we're looking for an element that might be in group 2A. Well, sulfur is underneath oxygen, so it is in group 6A. Calcium is in group 2A, and so that must be the correct answer. Iron and nickel are transition metals, right? Those are both transition metals. And potassium is in group 1A, so that's not the answer either. It's calcium. All right, number 11. Given the mass of an ionic compound, determine the number of ions of one of its individual components. If you have a 34.5 gram sodium azide, sodium nitride, if you have 34.5 grams of sodium nitride, how many sodium ions are present, right? Sodium ions, what's a sodium ion? It's Na+. Well, if we're starting out with 34.5 grams of Na3N, so that's sodium nitride, we're going to need the molar mass to do this problem, aren't we? We're going to need the molar mass to determine the number of moles of sodium nitride. And I've gone ahead and looked that up. It's 82.98 grams per mole. I don't know about you, but once you learn how to calculate molar mass and you're practicing at home, it's just a lot faster to Google it. You click on it, comes up with molar masses really quickly. So we know that in 1 mole of sodium nitride, we've got 82.98 grams of sodium nitride. Okay, that's great. And I'm sure that everybody who's hearing the sound of my voice is able to work that out. But what do we do next? If we were to stop here, we would simply have the number of moles of sodium nitride. But we know that in 1 mole of sodium nitride, we have did I write the formula incorrectly? Jeepers, Mr. Dean, what are you doing? There we go. There, I had it right the first 2 times. Anyhow, so Na3N. All right. Where was I? So we know that in 1 mole of sodium nitride, we have 3 moles of Na plus, right? Okay, think about it. Sodium nitride, what's it going to be made of? You're going to have the nitride on, and you're going to have 1, 2, 3 sodiums. Now, this is not an accurate representation because it's an ionic compound, but whatever. You get my idea that you have 3 sodium cations for every nitride anion. Okay, well, that's great. Now we've got the number of moles of sodium, but it's asking us for the actual number of ions. Well, the good news is that we know that in 1 mole of Na plus, how many ions are there? There's Avogadro's number of them, aren't there? 6.02 times 10 to the 23 Na plus ions. All right, so let's check our units now. We see that moles of sodium nitride cancel, moles of sodium cancels out, and we're left over with the ions of sodium. When you punch all that spinach in your calculator, you end up with a number that should have 3 sig figs. Let me double check my math here. Give me a sec. 35. There we go. We get 7.51 times 10 to the 23rd Na plus ions. And there's our final answer, that many ions. Okay, number 12. Given identical masses of 4 elements, determine which one has the least number of atoms. The higher the molar mass, the smaller the number of atoms present. The question says, given 15 grams of each of the following elements, which one would have the least amount of atoms? The way you can think about atoms, if atoms are spherical, which we like to imagine them as being spherical maybe, let's say you had 100 kilograms of bowling balls versus 100 kilograms of ping pong balls. Well, they're both spheres, right? A bowling ball is a sphere and a ping pong ball is a sphere. But if I have 100 kilograms of bowling balls, I'm going to have a lot less bowling balls than I will have ping pong balls, right? That's the difference between the elements, is their masses. Okay? So if I have 15 grams only, which one would have the least amount of atoms? It's going to be the heaviest one. Well, all I have to do is look up the molar masses on the periodic table. Carbon is around 12. Neon is around 20 grams per mole is what I should write here, grams per mole. Beryllium is the 4th element. It's around 9 grams per mole. And oxygen is around 16 grams per mole. Well, the heaviest one of these 4 is neon at around 20 grams per mole. So that's my answer. Number 13. Given a compound and the number of molecules, determine the mass of one of its individual components. What's the mass of phosphorus atoms present in 7.45 times 10 to the 22 molecules of diphosphorus monoxide? Well, I've got this many molecules. Okay, so that's almost a mole, isn't it? Well, let's see here. I've got 7.45 times 10 to the 23 molecules of P2O. And we know that there are 6.02 times 10 to the 23 molecules of P2O in 1 mole of P2O. But we also know that in 1 mole of P2O that we've got 2 moles of phosphorus. Okay. Now, if we were to stop here, we'd have the number of moles of phosphorus. So all I have to do is multiply this by the molar mass of phosphorus. I go to the periodic table and I see that there's 30.97 grams of phosphorus in 1 mole of phosphorus. Let's double check our units. Molecules of P2O cancel, moles of P2O cancel, moles of phosphorus cancel out, and I'm left with grams of phosphorus. So when I punch all that into my calculator, I get a mass of 7.66 grams of phosphorus when I have that many molecules of P2O. Number 14, if we're given a formula of a compound, determine the mass percent of one of its individual components. And she says, what's the percent of manganese in, this is gallium, dimanganese heptoxide is what this polyatomic ion would be here. Now this one's just kind of a pain in the neck, right? It's such a big molecule, or such a big compound, ionic compound, such a high molar mass, you'd have to tally the whole thing up, which I've already gone ahead and done. And the molar mass of this compound is 805.06 grams per mole, so that saves us a little bit of work. Now my question to you guys is, how many manganese atoms are there in one formula unit of this compound? Who could tell me how many manganese atoms do I have, or how many manganese do I have in this formula? That might be an easier way to pose it. Thanks, Julius. Julius is 100% correct. So what he's saying is, if you want the percent of manganese, okay, you're going to take the molar mass of manganese, which is 54.94 grams per mole, but you're going to multiply that by 6, right? We have 2 times 3. 2 times 3 is 6. So we have that times 6, and then we divide that by the entire molar mass, which is 805.06 grams per mole. You can see that grams per mole cancel out, right? But this is just a percent. We're going to multiply that mole fraction, or that fraction rather, that mass fraction by 100%. And we end up with what? 40 point, well, I could use more sig figs than that. But anyhow, what I have written down in my answers is 40.9%. Technically, I could use 4 sig figs here, couldn't I? Anyhow, 40.9% of manganese in this ionic compound. All right, number 15, given a hypothetical compound's ratio, determine the mass percent of one of its components. A compound has a ratio of 1 carbon for every 3 hydrogens. What's the mass percentage of carbon? Well, I don't think this one, I don't like to say easy in chemistry class, but I think this is pretty reasonable. If we want to know the mass percent, so mass percent of carbon is going to be equal to the mass of carbon divided by the total mass, right? Total mass of everything multiplied by 100%. If I have 1 carbon, well, the molar mass of a carbon is 12.01 grams per mole. The mass of everything is going to be the mass of the 1 carbon plus the mass of 3 hydrogens. Hydrogen has a mass of 1.01 grams per mole. And so that means I've got 12 divided by 15 approximately. And then I multiply that by 100. And when you do that, I keep leaving out my multiply by 100. There we go. Multiply by 100%. And you end up with a percentage. Can use 4 sig figs, 79.85% roughly. Actually, that's not very rough, is it? It's that percentage by mass carbon. So we're just determining mass percent in this problem, nothing more than that. Okay, mass percent. The mass of whichever component of interest divided by the total mass, multiplied by 100. Okay, let's switch gears a little bit and talk about the electron. It says, given the wavelength, determine the energy of a photon. You should have a couple formulas memorized. You've used them so many times. The energy is equal to Planck's constant times mu, or E is equal to hc over lambda, right? Because frequency is equal to, right? Frequency is equal to Planck's constant. Planck's constant times the speed of light. Sorry, I was like, that's not right. Frequency, sorry, I'm going too fast, is equal to speed of light divided by the wavelength. There we go. All right, that's a little bit better. Okay. It says here, given the wavelength, determine the energy of a photon. We've got our wavelength in nanometers. Of course, we're going to have to convert that into meters. And we're going to use this formula right here. I will provide you with Planck's constant, and I will provide you with the speed of light. I'm sure a lot of people have those memorized anyway. So we write that our energy is equal to Planck's constant times the speed of light divided by the wavelength. Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Speed of light, we have 3 sig figs, so let's just use 3.00 times 10 to the 8th meters per second. We have to convert our wavelength from nanometers into nanometers. But remember that 1 nanometer is equal to 1 times 10 to the negative 9 meters. So we can just slap that on there. 732 times 10 to the negative 9 meters, like that. Look at this beautiful stuff. Look, meters cancel out, seconds cancel out, and I'm left over with joules, which is a unit of energy. So I punch all that into my calculator, and I end up with an energy of 2.71 times 10 to the negative 19 joules for that one photon with that wavelength of 732 nanometers, which falls in the visible spectrum from 450 to 750 roughly. Anyhow, next one's got a typo in it. I noticed earlier today. So this should be NL, ML, and MS. It says conceptual understanding of the relationship between energy and quantum numbers in multi-electron systems. In English, what do quantum numbers really tell us? Well, I think that you don't have to know anything more than N is the principal quantum number, and it tells us about the size. Okay, L is the angular momentum. Momentum quantum number, and it tells you about the shape of the orbital. Next one is the magnetic orientation. So angular momentum, and then we have, sometimes we just call this the magnetic quantum number, and that tells us about the orientation, right? And the last one is the electron spin. So this is just electron spin, which can be plus a half or minus a half. Okay, so we'll put here direction of spin. Okay, number 18. Determine from a beautiful list of sets of quantum numbers which is an allowed set of quantum numbers for a 5D electron in the ground state of Mercury. Well, you remember the SPDF is when we have an s orbital. That's when we have an L of 0, 1, 2, 3. So that means our L is going to be 2. And that when we have a 5D, that the 5 represents the principal quantum number. Okay, so we're looking for a 5 and a 2. So that's going to disqualify the first two. Here we have a 5 and a 2 and a 5 and a 2. But there's a major problem with C, isn't there? Right? There's a really big problem with C. Because if L is equal to 2, ML cannot be equal to negative 3. That's impossible because ML is going to be equal to, and remember that they go in the order of N, L, ML, and MS, like that, okay? Remember that ML is going to equal negative L all the way up to 0, all the way up to positive L. So there's no way it could be negative 3. The lowest it could be would be negative 2, and that means that this one is going to be correct. Everything is copacetic in D. All right. There you have it. Number 19. Determine the ground state electron configuration of transition metals. What's the electron configuration of molybdenum with a 2+ charge? First, we can find molybdenum on the periodic table. It's element number 42. So molybdenum is element number 42. I don't know if that'll help you out. But anyhow, let's just do the shorthand. So we'll do molybdenum. The noble gas that precedes molybdenum is krypton. So what comes after krypton? So if you look after krypton, then you have rubidium and strontium. So those are in the 5s orbital. So that's a 5s2. Sorry, just check something out here. All right, sorry, where was I? So we have molybdenum. Molybdenum has an electron configuration of 4. Sorry, where am I? 5s2, 4d5. So 1, 2, 3, 4, 5. So 4d5. And if we have molybdenum 2+, we're going to remove 2 electrons, and then we have, sorry you guys, Mr. Dion can't see his periodic table. I have it on my wall. Yeah, so it's 5s2, 4d, 1, 2, 3, 4. Yeah, Mr. Dion needs a new prescription pretty bad. So sorry about that. I couldn't even read that from where I was. Anyhow, so remember that molybdenum falls under chromium. So we know that this is actually not the correct electron configuration, right? We borrow one from here and put it in there. So the correct electron configuration is 5s1, 4d5, right? Remember the rule for chromium and molybdenum, and then we looked at copper, silver, and gold, and the rule there. So that's the electron configuration. Then if we want to lose 2 electrons, okay, so if we want to find the electron configuration for molybdenum 2+, we're going to have to remove 2 electrons. Now there was a rule, the first in and the first out rule is what they call it. So since these ones went in first, those are going to be the first ones to come out. So we're going to take the electron from the orbital with the highest principal quantum number first, and so we would take out the 1s electron, and then we're going to take an electron from the d because we have to lose 2 electrons, so it becomes krypton, and then 4d4 like that. All right. Maybe I need to print out a bigger periodic table. Or all right, what question am I on? Number 20. Okay, let's go. Number 20. Given an orbital filling diagram, determine the identity of the atom. So here's our orbital filling diagram. So which ground state atom has an electron configuration described by the following orbital diagram? So we have argon, and then we have 4s2, 3d10, and 4p4, right? We have a total of 4 here. So if you go on the periodic table, so you start with 4s2, that takes you to calcium, and 3d10, that takes you all the way to zinc. And then if you have 4p4, 1, 2, 3, 4. Good, I can see this time. Anyhow, it's element number 34, and it is selenium. Okay, you got to know a little bit about the periodic trends. So given a periodic trend, determine why it happens that way. Why does atomic radius increase going down into the left? Well, atomic radius increases going down into the left. So the bottom left-hand corner, well, it's because as you go down, principal quantum number increases and effective nuclear charge decreases. Why does electronegativity increase going up and to the right? Well, it's because it's the opposite. You have a smaller principal quantum number, and so the atoms are smaller, and then you have a higher effective nuclear charge. So it's going to pull the electrons in tighter. Remember effective nuclear charge. So if you're not familiar with effective nuclear charge and you have to review it, that's Z effective, so effective nuclear charge. Number 22, given a list of atoms, determine which one has the highest specified periodic property. For example, which one of these has the highest effective nuclear charge? Remember that ZF increases going across like this, and it also increases going down like this, only a little bit. Let's see here. So we have arsenic, selenium, strontium, and barium. So let me just try to place these. Arsenic, so we have arsenic over here, and then we have selenium next to it. We have strontium and barium. So strontium and barium are lower, and they're way the heck over here. So you have strontium and barium. Okay, so selenium is definitely going to have the highest effective nuclear charge of all of those. Which ion has the largest radius? Remember that negative charges result in higher or larger radiuses than positive charges, so we can cross those two out. And then if we compare sulfur or sulfide and chloride, well, remember that it goes sulfur, chlorine, and argon like that. So both of these S2 minus and SCl minus, they're both isoelectronic with argon, right? They both have 18 electrons, but since this one has more electrons in the outer shell, they're going to repel each other more, and they're going to take up more space. And so they're also going to have less of an effective nuclear charge because you have more electrons and less protons, or more electrons per proton in the nucleus is what I. All right, there we go. Next page. I'll slow down a little bit here. Which atom has the largest first ionization energy? Remember that ionization energy is defined as the amount of energy required to remove an electron from an element in the gas phase, and ionization energy increases as we go from left to right across the periodic table. It also increases going up this way, right, as the elements are smaller. And so if we compare these elements, what do we got? We got calcium over here. We've got oxygen, which is up here higher, and we have carbon over here, and then we have beryllium, which is way over here. Well, based on my trend, oxygen is definitely going to be the highest. So there we go. Number 23, given successive ionization energies determine the identity of an element. Which period 3 element, so something in the third period, has these successive first through sixth ionization energies, which are all measured in kilojoules per mole? All we have to do is, examine these. You go from 578 to 1800, then you go to 2700, and as you go from, the third one to the fourth one, you see there's a huge jump here, right? Going from 27 to 11,500. Then they kind of stabilize again here. And so that means that this, whatever element this is, it has 3 valence electrons. Well, if we look at the third period, it goes sodium, magnesium, and then aluminum. After aluminum, we have silicon, and then phosphorus, and then sulfur and chlorine and argon. But if we count, we've got 1 valence electron here, we got 2, and then aluminum is 1, 2, 3, and so it must be aluminum, which is one of the answers, luckily. Okay, let's move on to number 24. Given a formula, determine the number of lone pairs on the central atom. My favorite topic, molecular geometry and Lewis structures. How many non-bonding electrons are on the central atom of iodine trichloride? So first we should tally up the total number of valence electrons. Iodine and chlorine are both in group 7A, so they all have 7 valence electrons, and there's 4 atoms total. 7 times 4 gives us 28 total valence electrons. We'll start with putting our iodine in the middle. We'll draw 1, 2, 3 bonds to chlorine like that. We'll fill up the octets of the chlorine. Now I've used up 8 times 3, which is 24. I'm going to have 2 lone pairs left over of 4 electrons. So I'll put 1, 2, 3, 4. And so the electron geometry here would be trigonal bipyramidal. The molecular geometry would be T-shaped. So Mg is T-shaped. That's not the question. It says how many non-bonding electrons are on the central atom. So there's going to be 4 non-bonding electrons, or 2 lone pairs. Number 25, given a Lewis dot structure, determine the formal charge on an atom. It's asking us what is the formal charge on the elements in this Lewis structure. This is supposed to be a triple bond. It's not really abundantly clear, I don't think. Or maybe I just can't see it. There we go. So if we calculate the formal charge on the silicon, silicon is in group 6. It's got 3 sticks and 2 dots. So that means it's going to have a charge of +1. Selenium is in group 6. Did I do silicon and say it was in group 6? Sorry, I got sulfur on the brain. My mistake. I was like, that doesn't make any sense when I started tallying up my formal charges. Okay, let's try that again. So it's silicon, which is in group 4. So it falls underneath carbon. So we have 4 minus 3 sticks and 2 dots. Sorry, there we go. We have a charge of -1 on the silicon. And then for the selenium, let's do the selenium now. Selenium is in group 6. There we go. So we got 6 minus 3 sticks and 2 dots. That gives us a charge of +1, and so we have a charge of +1 there. Whew. All right, let's move on to number 26. Conceptual understanding of resonance structure. So that's something you might want to look at. For example, the resonance structures of maybe the carbonate ion, which we looked at in class. Number 27, conceptual understanding of the relationship between bond length and bond strength, single, double, triple bonds. For example, if you compare, the bond length, let's say of, I don't know, if you have, let's say you have a carbon-carbon single bond, let's say in this molecule. So this is ethane, right? And then you compare that to a carbon-carbon double bond in this molecule, which is called ethylene. And then if you have a carbon-carbon triple bond in this molecule, which is called acetylene, and I don't expect you to know the name. But anyhow, right, as we go from here to here to here, the bonds are getting strongest, right? Strongest. But also, we have more and more orbital overlap, and so it's also the shortest, right? So that's a trend you want to know. In fact, one of the ACS finals a few years ago, that was the first question on the exam. Next one is, what's the molecular geometry of this ion, BrCl4 + 1? Well, let's tally up the total number of electrons. Bromine and chlorine, they're both in group 7A, so that's 7 times a total of 5 atoms. So that gives me 35 electrons, but I've got a +1 charge, so I'm going to subtract 1. 35 minus 1 gives me 34 total electrons. I'm going to start by putting my bromine in the center, and I'll put 1, 2, 3, 4 chlorines around it. I'll round out the octets of all the chlorines. That means I'm going to have used up 8 times 4, which is 32. I've got 2 electrons left over. So I've got 5 regions of electron density around my central atom. Now I'm going to fix it up here because it's asking us for molecular geometry, and I don't want to be the instructor who doesn't draw molecular geometries correctly. So I'll put the lone pair. I like to put them at the end of a line sometimes when I'm thinking about molecular geometry. There we go. Like that. And remember that molecular geometry only considers what? It only considers bonds, right? And so the molecular geometry of this ion, sorry, and I forgot my +1 charge on my bromine, the molecular geometry is seesaw. Okay, so seesaw. There is another name for it, and I know that some of the students put that in their report. It's called the distorted tetrahedron. Like that. Either one is totally fine. Number 29. You're given a list of 4 molecules. Determine the one with the tetrahedral geometry of jeepers. You got to draw a lot of structures here. You got radon tetrachloride, sulfur tetrafluoride, silicon tetrachloride, and phosphorus tetrachloride. All right, got a bunch of 3 tetrachlorides and 1 tetrafluoride. All right, well, I'm not going to, I don't know if I have the time to draw all of these, but the one that hopefully, you kind of pick up on the quickest is silicon tetrachloride, because silicon is in the same group as carbon, right? And carbon always forms 4 bonds, and silicon tetrachloride is going to look like this, right? It's going to have 1, 2, 3, 4 chlorines, and no lone pairs on the central atom, okay? So since it's surrounded by 4 regions of electron density, it's tetrahedral, right? If I look at the structure of radon tetrachloride, it's actually square planar. Okay, so maybe I could just write them out here. This is square planar. Sulfur tetrafluoride is seesaw. And did I draw phosphorus tetrachloride? No, let's do it. Okay, so phosphorus tetrachloride. How many total valence electrons do I have? I've got 5 from the phosphorus plus from the chlorines. I've got 14. There's something jacked up about this one. Oh, I know what it is. She's got a typo in here. It's full of freaking typos. It should be PCl4 minus, right? Because then it would make sense, right? You have 28 right? 5 plus 28 plus 1. So that's 29 plus 5, so it gives me 34. You'd have 34 total electrons. Let me just fiddle with it down here. You've got the phosphorus. You have 1, 2, 3, 4 chlorines like that. That means that you would have used up a total of 8 times 4, which is 32, 33, 34, like that. So that means that this one would also be T-shaped because you got 4 bonds to the phosphorus. And yeah, there you go. And then for the formal charge, phosphorus has 5 valence electrons, subtract 4 sticks and 2 dots, gives you a formal charge of -1. So you have a -1 charge there. So this one is in fact C. So, all right, number 30. Given a structure, use valence shell electron pair repulsion theory to determine bond angles on different elements. What are the bond angles of carbon 1 and the oxygen? Well, carbon 1 has 4 bonds to it, no lone pairs, so it's tetrahedral, and therefore the bond angles are going to be all around 109.5 degrees. They might vary a little bit, but not enough to matter for us. And then the oxygen has 2 bonds and 2 lone pairs. It's got a bent geometry. You know, as long as you know that the bond angle is a little bit less than 109.5 degrees, that's good enough for me. Okay. Yeah, there you go. Nothing more than that. You know, you could even do one better. You could do the bond angle at carbon 2, right? Because this is trigonal planar. So the bond angles are going to be around 120 degrees, give or take a little bit. Okay, number 31. Given a series of formulas, determine which molecule does not have planar geometry. Jeepers, they're making us draw a lot of ions here. So first we'll start with the phosphite ion. So the phosphite is PO3 minus 1. Phosphite looks like this. Okay. So here's the phosphite ion. So we have a +1 charge here, negative charge here, negative charge here. We got nitrogen trifluoride, so NF3, which looks like this. Trigonal pyramidal. So this one is not planar. Silicon hydride, Si2H2. It's gonna look something like this. I mean, it's saying here, which molecule doesn't have a planar geometry? Well, I would say that this one isn't planar either. This one's linear, right? Like the first one that I drew, this is trigonal planar. Trigonal planar. So I mean, that's a good answer. Oh, it does not have planar geometry. Shit. And then, so yeah, nitrogen trifluoride is trigonal pyramidal, so that's not planar. I'd say this is also a legitimate answer too, because that's linear, right? So we'll put linear on here. And then, what else? Aluminum chloride, rather, is looks like this. There's no such thing as aluminum trichloride, it's aluminum chloride. Sorry, Mr. Dion is talking fast and I'm not thinking. There we go. And it's trigonal planar as well. Okay, so trig planar, right? And nitrogen trifluoride was trigonal pyramidal. All right, there we go. Well, so we had 2 that are planar, right? We had A and 1 and 4 are both planar. Okay, let's move on from there. Let's see here. It's always good to have scratch paper when you're working on molecular geometry. Be able to differentiate between electron behavior in polar covalent versus non-polar covalent versus ionic bonds. You got to know the difference between them. I mean, you know, it's one of those things. If you look it up in a different textbook, you're going to get different answers, right? Normally, we think of non-polar covalent as having, you know, we're thinking about differences in electronegativity. You know, non-polar is going to be roughly less than, you know, 0.5. Some books will say less than 0.4. Polar is going to be somewhere in the neighborhood of 0.5 to 1.9 or maybe 2, right? Ionic is going to be greater than 2 or 1.9. Remember that there's no such thing like, there's no exact cutoff, right? So polar covalent is when we have an unequal sharing. Non-polar is when we have completely equal sharing. For example, for a non-polar covalent, that would be something like we looked at the other night, just bromine, right? Both of those elements have the exact same electronegativity. Polar covalent, that would be something like, you know, the bonds in H2O and water. What else? And ionic stealing. Well, it's just, you know, it's not sharing, right? One of the atoms is going to take all the electrons to form an anion. One's going to lose its electrons to become a cation. So that would be something like, you know, sodium chloride. Okay, number 33. Given a set of molecules, determine which molecule will be polar. And these are just some rules here. You know, one of the quick and dirty rules, if you ever get confused or lost or you run out of time on an exam, this is a great rule. If you have lone pairs in the central atom, not always, right? You cannot follow this. This is not 100% true, okay? It says lone pairs in the central atom means that it's polar. There are very few exceptions to that, though. We don't look at a ton of exceptions to that. Like one would be like the I3 minus ion, right? That's linear. And it does have lone pairs in the central atom, and it's not polar. But again, we don't look at many examples of that. So if you're ever scared, you know, you're like, what do I do? Okay. Usually, if there's lone pairs in the central atom, it's going to be polar. Usually. Which molecule has a permanent dipole? If we look at aluminum fluoride, so AlF3, it's trigonal, planar. I'll even leave out the lone pairs. So that's non-polar. So non-polar, right? All the dipoles are going to cancel. I've got a dipole going this way, this way, this way, and they all cancel each other out. They're all going in equal and opposite directions. If I look at silicon tetrachloride, SiCl4, right? That's a tetrahedral molecular geometry. I do have polar bonds, but again, they're all in equal and opposite directions. They're going to cancel out. Silicon dioxide, SiO2, is going to look like this. It's right. It's like an analog of carbon dioxide because silicon is in the same group as carbon. So we're going to have dipoles, but those are pulling in equal and opposite directions. They're going to cancel. But if I draw the Lewis structure of selenium oxide, or selenium dioxide rather, okay, so what's that going to look like? It's going to look something like this, or if you draw SeO2, you're going to see that you have a lone pair on the selenium. What does that mean? It means that the selenium is surrounded by 3 regions of electron density, and it's actually going to have a bent shape. So now I've got a dipole going this way and a dipole going that way, and the net dipole is going to be going in this direction. And so this is a polar molecule, and so the answer is selenium dioxide. Number 34, given a list of bonds, determine the bond that is the most polar. Well, luckily, all of these are bonded to fluorine, right? And fluorine is the most electronegative element in the periodic table, right? We're looking for the greatest difference in electronegativity. Now, fluorine has a value of 4.0. Even if we don't know the values of all these other elements, good news is that we know the trend, right? We know that electronegativity increases going across a period and going up a group. So increase in electronegativity. Well, if I identify where all of these other elements are, I've got germanium somewhere down here. Then I have sulfur, kind of kitty corner to it. I got phosphorus, and then I've got silicon, which is on top of the germanium, right? These are all really close to each other. So the one that's most to the bottom and to the left, which is germanium, is the least electronegative, and so it's going to have the most polar bond. All right, number 35, given a structure, determine the number of sigma and pi bonds. Remember that all single bonds, right? Any single bond like that, in the first bond, in the double bond, those are sigma bonds. Okay? After a sigma bond, anything after that is a pi bond. So I have a pi bond here, 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 and that's it. So that means I have a total of 4 pi bonds. Okay, all my other bonds are sigma bonds. Let's tally them all up. But remember, this is a condensed structure. You're going to have to follow me pretty carefully here. Look, how many do I have with CH3? Well, that CH3 is actually CH3, right? They're not drawn, they're condensed, but I know I've got 1, 2, 3. That means I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Why did I count an extra one? Because I'm supposed to only have 32. Shit. Somewhere I counted an extra one. Bruce asked me how many pi bonds are in a triple bond, right? If you have, right, the first bond is always a sigma. So in a triple bond, you have 2 pi bonds. All right. Anyhow, let me tally this up again. 1, 2, 3, 4, 13, 15, 16, 17, 18. No shit, it's not gonna work. 6, 7, 8, 9, 10, 11, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 30, 32. Well, shoot, now I'm counting up 33. Did anybody else get 33? Done it twice. And in my answer key, I say that I've only got 32. Yeah, why do I say 32? What the heck am I screwing up here?
I'm only counting 19 sigma bonds.
Well, there's definitely more than that, right? Because this is 3 sigma bonds. So 1, 2, 3,
Oh,
4,
whoops.
5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. No, there's a mistake. It's got to be 33 because there's also a sigma bond in here. I'm going to go with 33 sigma bonds. All right, there we go. Given a molecule, determine the hybridization of specific atoms. All right, so it's asking us to determine the hybridization of this carbon with the arrow next to it. So this carbon right here, it's got 3 regions of electron density around it. Remember, a region of electron density can be a single bond, it can be a double bond, it can be a triple bond, it can be a lone pair, or it can be a radical, an unpaired electron. So since there's 3 regions of electron density, 3 reds, so to speak, that means that this is sp2 hybridized. And if you're unsure about that, you might want to look in our textbook at table 10.4, which covers this very subject. All right, let's keep moving here. Well, Bruce, I don't know what the heck I'm doing wrong, but I'm counting an extra one in there somewhere, and I don't know where I'm counting an extra one. Yeah, I don't know how I'm counting that many anyhow. Okay, so in the answers before, I said that there's 32. So it must be 32 anyhow. I'm counting an extra one. I don't know where, anyhow. Conceptual understanding of pi bonds, they only happen between unhybridized. So when it says pure, that means unhybridized p orbitals. So you should know that the pi bond is formed by a side-to-side overlap of p orbitals like this, right? They overlap side to side like that. Number 38, given 4 chemical formulas, determine the substance with the highest boiling point. So the highest boiling point is going to be the strongest intermolecular forces. Hint, it's the one that can hydrogen bond, okay? So if I look at all of these here, I mean, these two here are hydrocarbons, so they're non-polar. Remember, I've told you this like 10,000 times this semester that carbon, hydrogen, and carbon-carbon bonds are non-polar. And so any molecule that has only carbon and hydrogen in it is a non-polar molecule. No exceptions to that rule. If you look at the next two, they're both capable of hydrogen bonding, right? They both have a hydroxyl or an OH on them, okay? But this one has a longer chain. It's just a heavier molecule. And so the bigger one that can hydrogen bond is going to have the highest boiling point, the strongest intermolecular forces. The next one says, recognize how strong electrolytes behave in water pictorially. They look like this. All it means is that they break up into their ions. Okay, so say for we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, 1, 2, 3, 4. Yeah. So I mean, the idea would be something like this. Like say you dissolved sodium chloride in water, you know, into some kind of vessel. Well, you're going to have individual, you know, sodium ions floating around, right? And you're going to have individual chloride ions floating around in the solution as well. All right. Here's my vessel. Okay. Given an equation, balance equations using the smallest set of numbers. So we have 1 zinc over here, and we have 3 here. So that means we at least have to have a 3 here. We've got, what else? We got 3 potassiums here. We got 1 potassium over here. We have 1 phosphorus, and we've got 2 phosphorus over here. So if I put a 2 here and then a 6 here, that balances it out. Check. So 2, 6, 6 and 6. So I have 12 oxygens over here. And then on this side, I have 6, yeah, so 12 oxygen. Good, it's balanced. All right. Number 41. Shown here is the balanced molecular equation that would occur between calcium chloride and sodium carbonate. Which of the following is the balanced net ionic equation? Well, if calcium carbonate is a solid, then hopefully you've kind of picked up on this by now that the net ionic equation would just include those elements, or that element in that ions, or those ions, shit. So you'd have calcium 2 plus carbonate 2 minus aqueous gives you calcium carbonate solid. So if I look at these, it would be 3. All right, there we go. Number 42, given the concentration of a compound, determine the concentration of ions. It says, what's the concentration of potassium ions in 2.47 molar potassium phosphite? Well, we know that we have 2.47 moles of K3PO3 in 1 liter. Okay, but we know that potassium phosphite is going to break up into 3 potassium ions, right, plus 1 phosphite ion, like that. And so that means that you're going to have 3 times 2.47 moles of K plus in 1 liter of the solution. So if I multiply 2.47 by 3 and then divide that by 1, I end up with 7.41 molar K plus ions in my solution. All right. What's the concentration of 200 and 50 milliliters of cesium made with 4.27 grams of cesium chloride. So first you're going to need the molar mass of cesium chloride, which is 168.35, so 168.35 grams per mole. Well, we know that concentration of our cesium chloride is going to be equal to the number of moles of cesium chloride divided by the volume of the solution. So let's figure out the number of moles of cesium chloride. It's 4.27 grams divided by 168.35 grams per mole. That's our numerator. We divide that by the volume. 250 milliliters. We know there's 1,000 milliliters in a liter, so that's 0.250 liters. There we go. We punch all that spinach into our calculator. We end up with a 0.101 molar solution of cesium chloride. Number 44, prepare dilutions. What volume of 1.55 molar is required to prepare 1,350 milliliters of a 0.750 molar solution? This is one of those great problems where you can use the formula M1V1 is equal to M2V2. We're doing nothing more than a dilution. We want to solve for the volume of 1. It's going to be equal to M2 times V2 divided by M1. So our M2 is going to be 0.750 molar. Our V2 is going to be 1,350 milliliters. And our initial or our stock solution is 1.55 molar. You see that concentration cancels out, and we end up with a volume in milliliters, which is 653 milliliters or 0.653 liters. Either one is totally fine with me. Number 45, given a neutralization reaction, so an acid plus a base, determine the amount of reactant required to completely neutralize the other reactant. If I've got what concentration of 32 mils of barium hydroxide solution is required to completely neutralize 150 milliliters of 0.425 molar nitric acid. Well, the first thing we need is a balanced equation, because we need to know for every mole of nitric acid, how many moles of barium hydroxide are we going to need, right? Because we've already got the volume of the barium hydroxide. And if we want to know the concentration of our barium hydroxide, it's just going to be equal to the number of moles of barium hydroxide divided by the volume. And we've already got the volume. So we just need the number of moles. So let's write a balanced equation. We've got barium hydroxide is aqueous plus nitric acid, which is aqueous. Remember, we're going to get a salt and water. The salt that we're going to get is barium nitrate, which is BaNO3. We're going to need 2 of those because nitrate has a charge of -1. Barium is in group 2A. There's a charge of +2. So we get barium nitrate, plus we're going to end up making H2O. Now we need to balance that out. I need a 2 here because I've got 2 nitrates. And I'm going to need a 2 here to balance that all out. Now I'm ready to go, because I know that I'm starting out with 150 milliliters of my 0.425 molar nitric acid. I'm going to convert this volume into liters. It's 0.1500 liters. So I'm starting with 0.1500 liters of HNO3. I know the concentration is 0.425 moles of HNO3 in 1 liter of HNO3. And I know that for every 1 mole, for every 2 moles, of nitric acid, HNO3, I need 1 mole of barium hydroxide. There we go. All right, that looks good to me. So when I work all that out, that's going to give me the number of moles of barium hydroxide, won't it? Yes, absolutely will. And I get that it's 0.03188 moles of barium hydroxide. Now I can just plug this number into my equation that's rather small up here, but I have 0.03188 moles divided by my volume, 32 milliliters. What's 32 divided by 1,000? You move the decimal over 2 places, and you get 0.00323200 liters. Sorry, it's kind of hard to read. I'm writing really small here, and we end up with 0.9963 molar barium hydroxide. So that's my final answer. Number 46 is just conceptual. If you're given a pictorial representation of a reaction, determine the amount of reactant needed. Yeah, that's something you might want to look at in the book. It's just, looking at the number of ions or molecules in a flask. Number 47, given amounts of 2 reactants, determine the limiting reactant. Amount of product formed. It shouldn't say product produced, product formed. And amount of excess reactant. If I've got 300 molecules of copper and 200 molecules of aluminum oxide react, how many molecules of copper 2 oxide are produced? Okay, well, the first thing I'm going to need is a balanced equation. And they give me a balanced equation right here. Notice that, it's shown down here. Yeah, is this the same question, just written twice here? All right, so if I write this out, why don't I rewrite it here? If I have 3 copper plus aluminum oxide gives me 3 copper 2 oxide plus 2 aluminum. There's my balanced equation. Well, what am I starting with? I'm starting with 300 molecules of copper and 200 molecules of aluminum oxide. All right, now since I have a ratio of 3 to 1 for my for my copper to my aluminum oxide, that means that my copper is going to be my limiting reactant, isn't it? Right? Now, that one I'm kind of just solving in my mind, but think about it. If I react all of this copper, right? If I remove all of those molecules, how many molecules of aluminum oxide are going to react? Well, remember, we've got 300 molecules of copper, right? And we know that for every 3 moles of copper, we produce 1 mole, or we consume 1 mole of aluminum oxide. So that means we only remove 100 of those. So we only lose 100. That means that copper is my limiting reactant. So copper is limiting reactant. How many molecules? What is the amount of excess reactant? Well, when I tally this up, so this is initial, this is change, this is final, I'm going to have no copper left over, but I'm going to have 100 molecules of copper left over. So I'm going to have 100 molecules of, sorry, not 100 molecules, but I'll have 100 aluminum oxide formula units left. So 100 Al2O3 in excess. All right.